Bismillah, alhamdulillah, salatu wassalam ala rasulillah. In this section 11.3, we will study inverses of matrices. We will start by defining the inverse of a matrix. What is it? And we will see together how to find the inverse of 2 by 2 matrix and in general for n by n matrix. Finally, we will see how to solve matrix equations by using the inverse of a matrix. We will start by revising these definitions that I have introduced to you in 11.2. What do we mean by square matrix? It is the matrix that has the same number of rows and columns. The main diagonal of a square matrix is the entries of the matrix that whose numbers of rows and columns are the same: A11, A22, A33, A44, and so on. The identity matrix, it is a square matrix, n by n matrix, that its main diagonal entries are ones and the other diagonal and the other entries are zeros. This is, of course, usually denoted by in. N here indicate the dimension, n by n, like this. This is 2 by 2, we will call it I2. This is 3 by 3, we will call it I3. This is I4. What is the importance of the identity matrix? In fact, it is clear from its name. It is the identity of multiplying matrices. So if you multiply a matrix by the identity matrix, you will get the matrix again, no change. This is why they call it the identity matrix. It does the job of the one for numbers. You know, if you have a number and you multiply it by 1, you will get a. So this is like the one of matrices. In is the one of matrices. Again, its importance comes from multiplying a matrix by the identity matrix. It gives the same matrix. You can here expect what is the result without operating or performing the multiplication here. No need to multiply. If you did, you will be the same. If you multiply the first row by the first column, you will get 1 because the other will be zeros. But it should be clear for you that this is a matrix and this is the identity. So for sure that the result will be the matrix itself. The another important property for the identity matrix that it is related to the definition of the inverse of a matrix. So it is now time to introduce the inverse of a matrix. What do you think? What do we mean by the inverse of a matrix? What would it be if there is an inverse for a matrix? You can remember that for numbers. For numbers, we have two types of inverses. We have the additive inverse, we have the multiplicative inverse. In fact, the inverse that we mean here is the multiplicative inverse. We know that for numbers, the multiplicative inverse of a, it is a to the power -1, which is in fact the reciprocal, 1 over a, which will give you 1 if you multiply. For numbers that they are not 0. What is the case if in the case of matrices? So what is the matrix that if we multiply by the matrix, we will get the identity? This matrix here will be called the inverse of the matrix. So if we have a matrix like that, whether from the right or from the left, we will call it the inverse. So if you have n by n matrix, of course here we are talking about square matrices because also the inverse function proper, the inverse matrix, it is a property for square matrices. And you know that the identity matrix itself, it is square matrix. It is n by n. Now, if you have two matrices and the product of them, whether you multiply them from the left to the right or from right to the left, AB or BA, in both cases, it is equals to the identity matrix. If you have such matrices like this, then these matrices are inverses of each other. So you can say that B is the inverse of A, or you can say also that A is the inverse of B. Okay, just it is about finding two matrices, their product is the identity matrix. So it is not the reciprocal like the case of numbers. So it is not about, there is no definition, of course, for this, because this is a number and this is a matrix. So this concept is not, this terminology is not used. And of course, the sense of division here is not also well defined in the same sense for numbers. Let me remind you that we have defined the addition and subtraction for matrices, the multiplication in special way, the multiplication of matrices. But for dividing matrices, we don't have such concept. In fact, you can think about it like A multiplied by the B inverse, the inverse of B. And this is, of course, what you will learn how to find today. So you can think about it like an alternative way or an equivalent way for dividing matrices. Let's introduce the formal definition. So if A is n by n matrix, so we don't have inverses for other matrices, that they are not square. If there exists n by n matrix, then if we have a matrix n by n, A, then if there exists a matrix n by n, let's denote it by A inverse, and the product of A and A inverse is equal to the identity, then this is the inverse. Why he said here if there exists? Because not all the matrices has an inverse, as we will see. Not all the matrices have an inverse. Let's start with this easy example about verifying. If you have two matrices, how to know that if they are inverses of each other or not? Just multiply them. Multiply them. If the product of them is the identity matrix, then they are inverses of each other. So let's multiply. Do you remember how to multiply? Matrices, the first row by the first column, then the first row by the second, and so on. This is 11.2. Revise it if you don't know how to do that. Look at the result of the product. It is the identity matrix. Is it enough just to multiply A by B? No. You know that in general, AB does not equals to BA in general. But here it must be. When we are talking about the inverse, we should have A multiplied by A inverse equals to A inverse multiplied by A equals to the identity. So here they should be equal. And this is why you need also to verify that they are also equals to the product of them equals to the identity matrix if you change the order of these two matrices. The question now is, you know how to verify. If you have two matrices, you can know that if they are inverses of each other or not. If the product is not the identity matrix, then they are not inverses. Now, how to find the inverse of matrices? If you have a matrix, let's start with 2 by 2. To find the inverse of 2 by 2 matrix, all what you need to do is to do the following. If the matrix entries are A, B, C, D, for an instant, then the inverse of this matrix will be D, negative B, negative C, A. What happens? We interchange the location of the main diagonal entries. They were AD, now they are DA. Then we change the signs of the another diagonal entries. Then after all of that, we divide it by this special number. This special number, in fact, it is called the determinant of a matrix. We will see that, inshallah, in 11.4. AD, which is just the product of the main diagonal entries minus the product of the another diagonal entries. AD minus BC. If it is 0, by the way, then this matrix has no inverse. It is not invertible. It has no inverse. If this is 0, because it will be 1 over 0 undefined. So inverse does not exist. So easy to find the inverse of 2 by 2 matrix. Be careful here. If the determinant is 0, then the matrix does not have an inverse. It is not invertible. And in this case, we say that it is singular. It is a singular matrix, not invertible. Does not have an inverse. look at the previous example here. It was clear that these two matrices are equal to each other. Look, 2 and 3, this becomes 3 and 2. We interchange the entries of the main diagonal. Also, we change the signs of the another diagonal entries. But where is the number here that we divided by? We should have here 1 over the determinant. In fact, if you look at the determinant, shortly we will write it like this, determinant of A, or we will use also this notation. It is just 2 times 3 minus 1 times 5. You can see clearly that it is 6 minus 5 equals to 1. So this is why you didn't see it there. Let's take an example. Here we have this matrix. We need to find the inverse, and we need to verify that it is really an inverse, that the product of them is the identity matrix. Just all what you need to do is to apply the method of finding 2 by 2 inverse matrix. All what you will do now, just you will say this is the inverse of this matrix will be equals to 3, 4, -2, -5. And here you will divide by 1 over the product here. It will be over 10 minus, in fact, you will start with the main diagonal. Look at the definition. It makes difference. If you said AD minus BC, it is not the same if you say BC minus AD. So be careful. We are multiplying the main diagonal entries first. So it is 3 by 4, which is 12, minus the another diagonals, 2 by 5, 10. And of course, this will give us the matrix 1 over 2. And here we have 3, -5, -2, and 4. You know that if you have a scalar, a number multiplied by a matrix, so you will multiply each entry by this number. So it will be 3 over 2, -5 over 2, -1, and 2. You can write it this way. And you can keep it. You have the option to keep it this way. It is the same. Now, I think it is easy to verify. Just he asked about it here. And it is, of course, better to make sure that you didn't make any mistake when you calculate the inverse. This is the verification process from the left and from the right. It is not a must, of course. Now, how to find the inverse of 3 by 3, 4 by 4, 5 by 5, n by n matrix? The idea is related to the elementary row operations that we have studied in section 11.3. In 11.1, we are in 11.3. So the idea is if you have n by n matrix, then what you will do to find the inverse, you will write what you can call the extended matrix. You will construct n by 2n matrix. This is your original matrix. You will write it here on the left. Then you will write the identity matrix on the right. So this is our original matrix, and this is the identity matrix. Then what you will do, you will use the elementary row operations that you have learned in 11.1 on this new large matrix. So this is now you will deal with this as a one matrix. You will apply the elementary row operations to change the left side to be the identity matrix here. Now what we will do, we will change this such that we will have here the identity. This one will be here. And a new matrix will be constructed here. That matrix that you will have, it will be the inverse. So in other words, this is a matrix. All what we will do, we will just write it in the row echelon form, in the reduced row echelon form. So we will make all these entries 1, and all of these are zeros. So these are 1, 1, 1, and these are 0, 0, 0, 0. Okay. And of course, the right-hand side in that case will be automatically the inverse. Let's summarize what we have here. The method of finding n by n matrix inverse. If it exists, of course, sometimes it does not exist, as you will see. So what we will do, step number one, we will write our matrix here on the left. We will construct the identity matrix here on the right. Then we will do elementary row operations. Do you remember we have 3 elementary row operations, multiplying a row by a number, then add it to another row and write the result in that row. The another way is to replace a row by multiplying that row by a number and change it to that number. Or we can interchange 2 rows. These are the 3 operations that we can do on this matrix. We will keep doing them until we have the reduced elementary, the reduced row echelon form. What is that? We will have the identity matrix here on the left, and what we will have here in the right will be a matrix. This matrix that will be here, it is the inverse of A. Actions are stronger than words. Let's do that with an example. Let A be this matrix. Find the inverse and verify that it satisfies the definition of the inverse. So what we will do, we will write the extended matrix. We will write our matrix here, 3 by 3 matrix here. And then we will write the identity matrix I3. This is I3, this is our matrix, and this is I3. We will write it on the right. Now what we will do, we will deal with this matrix as one matrix. So we have here 3 rows. This is 3 by 6. 3 rows, 6 columns. Now what we will do, we will apply the same elementary row operations that we have learned in 11.3. We need this to be 1, this to be 1, this to be 1, and all of these now to be zeros to have the identity matrix here. So we will just try to find the reduced row echelon form. So we are lucky, this is 1. All what we need now to make these zeros. So what we will do, you know what to do. Multiply the first row by -2, then add it to the second row, and multiply it again by 3, then add it to the third row. And this is what we have. We are lucky. This is 0, 0, 0, 1. Thank you. All what we need now to have this equals to what? To 1. So we will multiply the third row by third. And here we are. We are really very close now from having the inverse. But just we need this now to be zeros. By the way, it is very important to know, sometimes they will ask you just about, they will not ask you about the whole inverse. For instance, if they ask you about the sum of the entries of the last row in the inverse, here they are ready. This row will not be changed. Alas, we will stop here. We got 0, 0, 1. The third row will not be changed until the end. Now the change will be on the second and the first rows. So if he asked you about the sum of entries of the last row, here it is. Stop here. Now we need to continue. We need these to be zeros. What we will do? We can use the third row to eliminate these to be zeros. So for example, you can multiply here by -2, then add it here. You can multiply this by 4, then add it there. And then you will use this number to eliminate this. Or you can use also the second row to eliminate the first row. Look here, for example, if you notice that this is 2, this is 2. If we multiply here by just by 2 and add, you will get 0, 0 here. Now you need to eliminate this, use the third row. Multiply the third row by -2, then add it to row number 2. What is important that don't forget to do that on the 6 columns that you have. Look now at the matrix that we obtained here. This matrix is the inverse. It is the inverse. And you can verify that, of course, by multiplying. And the multiplication, by the way, is not difficult, because you can find easily that Again, it is unnecessary unless you are asked to do that. Keep it in mind that it is the main property of the inverse, the definition of the inverse. If you multiply the first row by the first column, you will get 1. Then if you multiply the first row by the other 2 columns, you will get zeros, and so on. As I told you, not all the matrices have inverses, because some matrices are not regular, they are singular matrices, they are not invertible, like this one. Look at this matrix. We will see in the next section a very nice criteria how to know that the function the matrix is invertible or not, just by finding the determinant. But let's now see a special way here to show us if the matrix is invertible or not. What to do to find the inverse, guys, of this matrix? We will write the extended matrix. We will write it here on the left and the identity on the right. Then we will apply the elementary row operations. Unfortunately, we don't have here 1. The first entry in the first row is not 1. So what we can do, someone of you may say we multiply by half. It is, in fact, a very bad idea, because you will bring here fractions. And you need to use now the first row to eliminate this 0 and 0. So you will deal with fractions, and this is not good. What you need to do here, in fact, instead of multiplying by half, it is better to interchange row number 1 by any row, 2 or 3. It is up to you. So let's interchange row number 1 and row number 2. This is one of the 3 elementary row operations that we have. Now we have the first entry here is 1. Now we can use the first row to eliminate the second and third row. So all what you need to do, multiply the row number 1 by -2, then add it to row number 2. After that, multiply row number 1 by -1 only and add it to row number 3. Look what we will have. Now we need this to be 1 and this to be 0, this to be 1 as much as possible, of course. So let's multiply the second row by -1/7. And here we are, this is 1. And now we can eliminate this, we make it 0. So we will just add the first row to the third and write the result in the third. Look what happens here. We lost the 1. We were planning to have here 1, but unfortunately it becomes 0. And in this case, we cannot have the identity matrix on the left, because whatever, even if you are able to eliminate these, it will not be at the end the identity matrix, because the identity matrix you must have here once. The main diagonal entries are ones. So this is not the case here. In this case, we cannot change the left half to the identity matrix, so the original matrix does not have an inverse. In general, if we encounter a row of zeros on the left, when we try to find the inverse, then the original matrix does not have an inverse. And as I told you, inshallah, in section 11.3, we will have a very nice criteria for the invertibility of a matrix. It is about the determinant. If the determinant is 0, the matrix is not invertible. It has no inverse. Let's now mention some properties of the inverse of a matrix. The inverse is unique. What is that? It means that if you have a matrix, it has only one inverse. There is no more than one inverse. The inverse of the inverse is the matrix itself. And this is, of course, clear, because if you have A times B equals to B times A equals to the identity, then A is the inverse of B, and B is the inverse of A. So think about A here, but put it inverse. So here you are, it will be A equals to inverse A inverse. So the inverse of the inverse is the matrix itself. The inverse of the product is not just the product of the inverse in the same order. No, In fact, the inverse of the product is the product of the inverses in a reverse order. So it will be B inverse A inverse. Be careful about that. And of course, you can prove that in general if you would like to. For the addition, you cannot distribute it over the addition. So the inverse of the sum of two matrices is not equal to the inverse of the first one plus the inverse of the second one. Be careful about that. So how to find the inverse of the sum? Find the sum. Let's say the sum is C. So this will be C inverse. Then the resulting matrix, find its inverse. In general, it will not be equals to the sum of the inverses of these two matrices. Now, this is a very important property. I would like to mention this, and I want to have your attention here. If you have two matrices that they are invertible, they have inverse, then if you have A, B equals to C, how to solve this equation for A or for B? What will be A? What will be B? A, if you multiply both sides by the inverse of B, you will have here A multiplied by the identity equals to C multiplied by B inverse, because B inverse is the identity. They are N by N matrix. And A by the identity, it is A. And be careful, this does not equals to B inverse C in general. So be careful, it makes difference. So A, it is CB inverse. And B also, B will be what? B will be, B is equals to A inverse C, not C A inverse. Be careful. Why is that? Because look how to find B in this case. To find B, you will multiply both sides by the inverse of A from where? From the left. You know that the product is not commutative. This is the identity matrix. The identity matrix multiplied by B will give you B. Clear? I wish it is clear. It is so important. It should be clear. The same here. If and this is very interesting property for matrices. If AC equals to BC, then A equals to B only if C inverse exists. For numbers, we know that this is always valid if unless, of course, the number is 0. You know, if you have AC equals to BC, and we are talking about here numbers, then of course this means that A equals to B if C is not 0. For the case of the for matrices, if you have AC equals to BC, and we are talking about matrices now, then what is the condition to have A equals to B? To have A equals to B, to cancel, you can think about it like the cancellation property. In fact, it is all about having the inverse of C. We have C inverse. So C inverse exists. So in that case, what you will do, you will multiply both sides by what? By the inverse. You will have AC multiplied by C inverse, BC multiplied by C inverse from the right. Then this will be the identity matrix. A multiplied by the identity equals to B multiplied by the identity, and then you will have A equals to 2B. I think it is now time to talk about matrix equations. We will use the idea that I mentioned here in this slide at the end of these two properties to solve matrix equation. What is the matrix equation? It is an equation that contains matrices. It's clear from the name. In fact, we can solve the linear systems that we have solved in 11.1 by using the Gaussian elimination. We can solve them by the method of the matrix equation by using the inverse of the matrix. How to do that? First of all, you need to convert this linear system into a matrix equation. How to do that? You will just realize that what you have here is just the product of this row with this column. So you will write here the matrix of the coefficients: 1, negative 2, negative 4, 2, negative 3, negative 6, negative 3, 6, 15. So this is the matrix of the coefficients, multiplied by the matrix of the variables x, y, and z, and put it equals to the matrix of the constants. Let's give them names. So if we can call this one A, and this is X capital, this is B capital, then we have AX equals to B. And this is the linear matrix equation that we are talking about. So you have a matrix A multiplied the matrix X equals to B. Of course, this is n by n, this is n by 1, this is n by 1, it will be. So now how to solve it? How to solve this matrix? To solve this matrix, it means that you have X. What will be X in this case? Of course, to find X, what you will do? You will multiply by A inverse from the left or from the right? From the left, because here it is. A inverse here, it is on the left, so we will multiply by A inverse from the left. Then we will apply, of course, the associative property. So A inverse by A equals to what? It will be equal to the identity matrix, and the identity matrix multiplied by any matrix give you the same matrix. Here we are. So X is the inverse of B. And of course, this means that if you have the inverse, for example, for this system, in fact, if you remember, we obtained this, the inverse of this matrix in the previous example, in example number 4. So now to find the matrix X, which is X, Y, and Z, just multiply the inverse by the constants, by the matrix of the constants, B. And here we are. This is X, this is Y, and this is Z. And these are the solutions of this matrix, of this linear system. Again, it is, of course, longer than the Gaussian elimination. So don't use it if you can use the Gaussian elimination, unless, of course, you are enforced to do that. Usually, if they give you a question to solve or a system to solve in using this method, it will be 2 by 2, 3 by 3 at most. Because you know the process of finding the inverse is a little bit long. We will see, by the way, I will show you another way to find the inverse in 11.4 when we study, after we finish studying the minors and the determinants. There is a nice way also. But if you are good in elementary row operations, you can do that easily, ya shabab. Now, how to solve a matrix equation in general? If you have A, X equals to B, A is n by n, X will be n by 1, B will be B1. Then if the inverse exists, the solution will be A inverse times B. If the inverse does not exist, in fact, this method cannot be used, and you need to use the Gaussian elimination in that case. Let's take it, as I said, ya shabab, for 2 by 2 system. Now, again, solving this system by the methods of 10.1 Gaussian, by using the elimination or the substitution, it is easier. But here you need to use the matrix equation. How to write this as a matrix equation? All what you need to do is to write the matrix of the coefficients multiplied by the matrix of the variables. The variables are X and Y, equals to the matrix of the constants. Here we are. Now, what are the coefficients? 2, 3, -5, -6. Now, to solve this matrix, in fact, the solution will be equals to the inverse of this matrix, 2, -5, 3, -6, multiplied by 15, 36. So it is all about the inverse of the matrix. How to find the inverse of this matrix? It is 2 by 2, easy to be found. I show you how to find the inverse of 2 by 2 matrix. So here we are. We will write it as a matrix equation. We will convert it from a linear system to a matrix equation. This is the inverse. The inverse, we will interchange the main diagonal entries, then we change the signs of the entries of the another diagonal. We will divide also by the determinant. What is the determinant? The product of the main diagonal entries minus the product of the other diagonal entries. And here we are. This is the inverse. You can multiply each entry by third, or you can keep it as it is. It is better here to keep it as it is to make the calculation easier. Why? Because now when you multiply, look here, we have a little bit big numbers. So the multiplication process will be a little bit longer. So what you can do, you can use the probability that if you have A times B multiplied by a constant K, let's say, then you can have it like A multiplied by K times B. The product, the scalar multiplication is commutative when you multiply by scalar, and is derivative and also associative. So you can multiply now the third by these entries to find that the result here is what. For example, here you can keep this as it is, -6, -3, 5, 2. Then here you have what? 5, and multiply by it will be 12. Now it becomes, of course, much easier to find that the product of the first row by the second column will give you 30, and the second row by the first column will give you 9. Now what you have here, X is 30, Y is 9. And of course, this is the inverse. This is the solution of this system. This is all what we have, Shabab, in 11.3. Let's summarize now. The summary of this section can be showed here in this slide. So you need to remember what is the identity matrix. It is n by n matrix, that its main diagonal entries ones and its the entries zeros. The product of the matrix by the identity will give you the matrix itself. The definition of the inverse, how to know that the matrix is an inverse of another matrix if their product gives you the identity matrix. The inverse of the inverse is the matrix itself. The inverse of the product is the product of the inverses in a reverse order. To find the inverse of 2 by 2 matrix, all what you need to do is to just look at the main diagonal entries, interchange them, and change the sign of the other entries. Then, of course, don't forget to divide by the determinant of the 2 by 2 matrix. If the determinant is 0, then this matrix has no inverse. Now, this is for 2 by 2. For 3 by 3 matrix, to find the inverse, you can follow this algorithm of solving or finding inverse n by n inverse matrix. Write your matrix on the left and the identity matrix on the right to have the extended matrix. Then apply the elementary row operations on this matrix until you have the reduced row echelon forms. What is that? It is having the identity matrix on the left and another matrix will be constructed on the right. This matrix, in fact, it is the inverse. To solve a linear system by using the inverse by the inverse matrix, what you need to do, you need to write it as a matrix equation. A is the matrix of the coefficients, X is the matrix of the variables, B is the matrix of the constants. Then the solution of this system will be equals to the inverse of A multiplied by B. Of course, if the inverse exists, you can have the solution in that case. If the inverse does not exist, you need to use another method. This method does not work to solve matrices if the inverse does not exist. You cannot use the matrix, the inverse to solve the matrix equation. And in that case, you need to go back to the Gaussian elimination to find your solution. As you will see and practice when we solve, inshallah, the recitation exercises tomorrow in the class of tomorrow, during tomorrow class. Okay, I think this is all what we have for today. Thank you and see you tomorrow, inshallah.